Yo, yeah. Oh, testing. Probably working. Oh. Is this shit working anyway? Probably. Testing. Yeah, everything works. Oh my god, okay. Yeah, the camera's flicking, whatever. Welcome to another stream, everybody. Today we started on a new freaking course. And that course, ladies and gentlemen, is called quantum mechanics. And quantum mechanics aren't a joke. Like, there's a lot to digest. And quantum mechanics is like if you understand quantum mechanics, you understand chemistry and the bonding and all that. So yeah, that's my new course. Am I gonna survive? I don't know. The exam is oral, so that's the first ever oral exam I will have in this university college thing. And yeah, I honestly, it's exciting and scary at the same time. And I also have another course called analytic chemistry, but whatever. I mean, it is what it is, man. But yeah, quantum mechanics. Anyway, we got 42 subscribers. 42. Appreciate all the support I've been getting. And yeah, this is only the start because I have something very big planned up. So stay tuned for that. And it's gonna be one of my biggest projects that I ever did in my whole life. So yeah. But yeah, welcome to the stream. This stream is basically gonna be preparing for my course. So I'm gonna read about matter, energy, and waves, as you can see on the title. So come along, read with me, and gain some knowledge about quantum mechanics because I understand zero about that shit. But yeah, I'm also been editing my video too about Newman projections. It should be out soon. Don't worry about that. And then I'm gonna continue with chair configurations. So cyclohexanes and configuration of that. So that's gonna be very good. But for now, we're gonna focus on quantum mechanics. Oh my god, I know I'm not gonna be flamed in that course. Like, quantum mechanics is so really hard. But yeah, let's get on with this. Let me see what we got here. Should be like this. But how you all been? How my chat? How you all been, man? Any exams coming up? Anything coming up? All right. This is the textbook. So basically, I have to read a lot. I have to read a lot. So, yeah, it's gonna be a little reading stream, just like we always did with medical chemistry. And what else did we do? Probably like something, I don't know. But yeah, we're gonna gain some knowledge together and just having fun with quantum mechanics. I don't know if you're gonna have fun with quantum mechanics, but it sounds interesting. And in first hand, I know a bit of quantum mechanics, like wave functions. That's pretty much it. So it's kind of interesting to gain knowledge and learn about quantum mechanics. Since it's very much relevant in learning chemistry, so yeah, it's gonna be good. But yeah, it's gonna be a chill stream, everybody. So yeah, I'm just glad I can stream with you guys because I feel comfortable reading also with you. And yeah. Anyway, let's get started. Let's get started. Okay. My English is not the greatest, but I'm trying. All right. So bear with me if I'm like stuttering or like all that shit. All right. All right. The presentation of physical chemistry in this text is based on the experimentally verified fact that matter consists of atoms. In this topic, blah 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 blah. Okay, nobody cares. All right, atoms. Atoms. Everybody know what the hell atoms are, right? Hopefully, yeah. So atoms is basically nucleus and protons and all that. So yeah, the atom of an element is categorized by its atomic number, Z. Huh, that's our community. Okay, okay. So Z, all right, Z, which is the number of protons in its nucleus. The number of neutrons in a nucleus is variable to a small extent, and the nucleon number, which is also commonly called the mass number, A, is the total number of protons and neutrons in the nucleus. Protons and neutrons are collectively called nucleons. Atoms of the same atomic number but different nuclear number are isotopes of the element. The nuclear model. According to the nuclear model, an atom of an atomic number Z consists of nucleus of charge Ze. Oh, that's literally us, Ze, our community. That's so cool. Anyway, surrounded by Z electrons, each of charge E, which is a fundamental charge inside the front cover, blah 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 blah. Okay. These electrons occupy atomic orbitals, which are regions of space where they are most likely to be found, with no more than 2 electrons in any one orbital. The atomic orbitals are arranged in shells around the nucleus, each shell being categorized by principal quantum number, n1, n2, n3, whatever. A shell consists of n2 or n squared 2 individual orbitals, which are grouped together into n subshells. These subshells are orbitals they contain are denoted sp, d, and f. For all neutral atoms other than hydrogen, the subshells are given shell have slightly different energies. Okay, where the frick? Okay, so it's like that. The periodic table, everybody. The periodic table. So the sequential occupation of the orbitals in successive shells results in periodic similarities in electron configurations. The specification of the occupied orbitals and of atoms when they're arranged in order of their atomic number. This periodicity of structure accounts for the formulation of the periodic table, seen at the back cover. Alright. The vertical columns of the periodic table are called groups, and in the modern convention, numbered from 1 to 18 successive rows of the periodic table are called periods. Alright. So the number of period being equal to the principal quantum number of the valence shell, the outermost shell of the atom. Some of the groups have also have familiar names. Group 1 consists of alkali metals. Group 2, more specifically calcium, strontium, and barium of the alkaline earth metals. Group 7 of the halogens, and Group 18 of the noble gases. Broadly speaking, the elements towards the left of the periodic table are metals, and those towards the right are non-metals. The two classes of substance meet a diagonal line running from boron to polonium, which constitute the metalloids, with properties intermediate between those or metals or non-metals. The periodic table is divided into sp, d, and f blocks according into the subshell that is last to occupy in the formulation of the electronic configuration of the atom. The members of the d block, specifically the members of groups 3 and 11 in the d block, are also known as transition metals. Those of the F block, which is not divided into number groups, are sometimes called the inner transition metals. The upper row of the F block, period 6, consists of lanthanoids, still commonly the lanthanides, and the lower, period 7, consists of the Alright. From ionic compound that consists of A, B, yeah. It's this one. Ions. A monoatomic ion is an electric charged atom. When an atom gains one or more electrons, it becomes a negatively charged anion. When it loses one or more electrons, it becomes a positively charged cation. The charge number of the ion is called the oxidation number of the element in that state. Thus, the oxidation number of magnesium is Mg2+, 2+2, and that of oxygen in O2- is -2. It is appropriate, but not always done, to distinguish between the oxidation number and the oxidation state, the latter being the physical state of the atom, which has specified oxidation number. Thus, the oxidation number of magnesium is +2 when the present is Mg magnesium 2+, and it is present in the oxidation state of magnesium 2+. The elements form ions that are categorized of their location in the periodic table. Metallic elements typically form cations by losing the electrons of the outermost shell and acquiring the electronic configuration of preceding noble gas atom. Nonmetals typically form anions by gaining electrons and attaining the electron configuration of the following noble gas atom. Alright. Molecules. A chemical bond is a link between atoms. Compounds that contain a metallic element typically, but universally, form ionic compound that consist of cations and anions in a crystal. Wait, what? Am I tripping? No. Form ionic compounds that consist of cations and anions in a crystalline array. The chemical bonds in an ionic compound are due to the Coulomb interactions between all the ions in the crystal, and is inappropriate to refer to a bond between a specific pair of numbering ions. The smallest unit of ionic compound is called a formula unit. Thus, sodium nitrate, that's nitrate, right? sodium nitrate, right? Consists of Na plus cation and NO3 minus anion. It's the formal unit of sodium. Oh, sodium nitrate. Okay. So I was right. Compounds that do not contain a metallic element typically form covalent compounds, consisting of discrete molecules. In this case, the bonds between the atoms of a molecule are covalent, meaning that they consist of shared paired electrons. What is this? A note of good practice. Some chemists use the term molecule to denote the small unit of the compound with the composition of the bulk material, regardless of whether it is an ionic or a covalent compound, and thus speak of a molecule of sodium chloride. We use the term molecule to denote the discrete covalent bond that entirety, as in H2O for ionic, blah blah blah. Okay, fine. Lewis structure, everybody. Lewis structures. We definitely know about that. I made a video about Lewis structure. I made a video about that. About bond line drawing. So check that out if you haven't seen that. The pattern of bonds between neighboring atoms is displayed by drawing a Lewis structure in which bonds are shown as lines and lone pairs of electrons. Pairs of valence electrons that are not used in bonding are shown as dots. Lewis structures are constructed by allowing each atom to share electrons until it has acquired an octet of 8 electrons. For hydrogen, a duplet of 2 electrons. A shared pair of electrons is a single bond. 2 shared pairs constitute a double bond, and 3 shared pairs is a triple bond. Atoms of element of period 3 and later can accommodate more than 8 electrons in their valence shell and expand their octet to become hypervalent. That is form more bonds than the octet rule will allow. For example, SF6, I guess. Or form more bonds to a small number of atoms. See brief. Okay. When more than one Lewis structure can be written for a given arrangement of atoms, it is supposed to that resonance, a blending of structures may occur and distribute multiple bond character over the molecule. For example, 2 covalent structures of benzene. All right. This is basically examples of Lewis structures. All right. Up orientations around the central atom that maximize their separation, then the position of the attached atoms, not the lone pairs, is noted and used to classify the shape of the molecule. Thus, 4 regions of electron density adopt the tetrahedral arrangement. I made a video about geometry. If you haven't watched that, I suppose you watch that so you understand what I'm saying, but hopefully it makes sense. Where was I? Noted used to classify the shape of the molecule. First, 4 regions that adopt the tetrahedral arrangement. All right. If an atom is at each of these locations, as in methane, then the molecule is tetrahedral. If there is one atom at only 3 of these locations, like in ammonium, then the molecule is triangular pyramidal. Figure found and shown in figure 1-2 is reference. Okay, yeah. So it's about Lewis structures. Okay, so so there's a level self-test, but the answer is there. So okay. Vesper theory. Expect in the simplest cases, a Lewis structure does not express the 3-dimensional structure of a molecule. The simplest approach to the prediction of a molecule shape is valence shell electron pair repulsion theory, Vesper theory. In this approach, the regions of high electron density as represented by bonds, whether single or multiple, and lone pairs. Oh, wait, what? Okay, so this. Okay, so there's linear, band, square, we know that. We know that's geometry. I already made a video about that. If you haven't watched it, I'll suggest you're gonna watch it. Polar bonds. Polar bonds. Holy shit, how much are okay. Polar bonds. Covalent bonds may be polar or correspond to an unequal sharing of the electron pair, which the result that one atom has a partial positive charge, denoted delta plus. This one right here, this thing right here is called the delta. So it's Greek, basically. So when you, yeah, basically math and chemistry, it's all about Greek letters. And the other, a partial negative charge, delta minus, or minus delta, or whatever you want to call it. The ability of an atom to attract electrons to itself when part of a molecule is measured by electron negativity, chi, chi of the element. The juxtaposition of equal and opposite partial charges constitutes an electric dipole. If those charges are plus q and minus q, they are separated by a distance d. The magnitude of the electric dipole moment mu is equals q and d. All right. Okay, bulk matter. Bulk matter consists of large numbers of atoms, molecules, or ions. Its physical state may be solid, liquid, or gas. A solid is a form of matter that adapts and maintains a shape that is independent of the container it occupies. A liquid is a form of matter that adopts the shape of the part of the container it occupies in a gravitational field, the lower part, and is separated from the unoccupied part of the container by a definite surface. A gas is a form of matter that immediately fills any container it occupies. A liquid and a solid are examples of condensated state of matter. A liquid and a gas are examples of a fluid form of matter. They flow in response to forces such as gravity that are applied. The volume, wait, what? Am I tripping? Oh yeah. Okay. The properties of bulk matter. The state of bulk sample of matter is. Thought someone was coming in. The state of a bulk sample of matter is defined by specifying the values of various properties. Among them are the mass m, a measure of quantity of matter present. Unit 1 kilogram is 1 kg. All right. How much that is in pounds? Is the okay? I think pounds. No. The volume V is a measure of quantity of space the sample occupies. Unit 1 cubic meter, 1 meter squared and 3. All right. The amount of substance N of measure of the number of specified entities, atoms, molecules, and formula units. 1 mole. Okay, 1 mole. Extensive property of bulk matter is a property that depends on the amount of substance present in the sample. An intensive property is a property that's independent of the amount of substance. The volume is extensive, the mass density, rho, with rho equals m divided by volume, or mass, mass divided by volume to get rho. Okay. Man, I hope I pass this quantum mechanics course, because I know, like, I heard a lot of people having this course before it's had a hard time with it. So either you pass or either you fail the course, basically. And it's oral. So there's gonna be 3 professors gonna judge my ass off when I write quantum mechanics. All right. So we have to lock in, like we have to upgrade, and I'm gonna upgrade a level up with you guys. So that's gonna be very much fun, and you might like gain some knowledge, hopefully, but who knows. Enough with my stupid ass explaining. Imagine like a video of me explaining quantum mechanics. I will rather like, yeah. The amount of substance N, colloquially the number of moles, is a measure of number of specified entities present in this sample. Amount of substance is the official name of the quantity. It is commonly simplified to chemical amount or simply amount. The unit 1 mole is currently defined as the number of carbon atoms in exactly 2 grams per carbon 12. In 2011, the decision was taken to replace this definition, but the change has not yet, in 2014, been implemented. The number of entities per mole is called Avogadro's constant, Na. The currently accepted value is 6.022 x 10 and 23 mole in 1 minus 1. All right. Note the Na is a constant with units, not a pure number. The molar mass of a substance, m units, formerly kilograms per mole, but commonly grams per mole, g mole minus 1 is the mass per mole of its atoms. Its molecules and its formula units, the amount of substance of specified entities in a sample can readily be calculated from its mass by noting n equals mass divided by the molar mass of substance. Okay, and then the pressure. All right, pressure. A sample of matter may be subjected to pressure P unit 1 Pascal. Pa 1 Pascal is 1 kilogram mR, which is defined as the force F. It is subjected to divided by area A to which the force is applied. A sample of gas exerts a pressure on the walls of its container because the molecules of gas are ceaseless. Random motion and exert a force will distract the walls. The frequency atmosphere. Bro, what happened to the stream? Bro. Am I lagging? Am I still lagging? Am I lagging? No, I'm not. Oh my god. Okay. Okay, I'm gonna skip all that. There's just subunits, SI units. We did already learned that in what is it called, in inorganic chemistry, my first course. So all of this just like revise, which is nice, but I already know all this. So okay, what the hell? Okay, checklist. Okay, yeah. So the gas equation, pretty important. Okay, so this is like a checklist. Okay, so in the nuclear model of an atom, negatively charged electrons occupy atomic orbitals, which are arranged in shells around the positively charged nucleus. The periodic table highlights the similarity in electronic configuration of atoms, which in turn lead to similarities in their physical and chemical properties. Covalent compounds consist of discrete molecules in which atoms are linked by covalent bonds. Ionic compounds consist of cations and anions in a crystalline array. Lewis structures are useful models of pattern of bonding in molecules. The valence shell electron pair repulsion theory, VSEPR theory, is used to predict the three-dimensional shapes of molecules from their Lewis structures. The electron in polar covalent bonds are shared unequally between bond nuclei. The physical states of bulk matters are solid, liquid, and gas. The state of sample of bulk matter is defined by specifying its properties such as mass, volume, amount, pressure, and temperature. The perfect gas equation is the relation between the pressure, volume, amount, and temperature of the idealized gas. a limiting law. It's a law that becomes increasingly valid in a particular limit. Maybe I can just read like the concept and that's pretty much it. Then I can get, okay, energy. This is some physics. So if anyone watching that are physics lovers, I appreciate you, but this is basically all for you. And technically, quantum mechanics is basically like physics a lot. And my weak point is physics. So, yeah, we'll see how that goes. Much of chemistry is concerned with transfers and transformations of energy, and from the outset it's appropriate to define this familiar quantity precisely. We begin here by reviewing classical mechanics, right? Which was, am I lagging? Hopefully I'm not lagging. Yeah, probably. Okay, hopefully I'm not saying the word. Much of chemistry mechanics, which was formulated by Isaac Newton, my god, in the 17th century, and established the vocabulary used to describe the motion and energy of particles. These classical ideas prepare us for quantum mechanics. Oh, the more fundamental theory formulated in the 20th century of the study of small particles such as electrons, atoms, and molecules. We developed the concept of quantum mechanics throughout the text. Here we begin to see why it's needed as a foundation for understanding atomic and molecular structure. Alright, buddy. Force. Molecules are built from atoms and built from subatomic particles. To understand their structures, we need to know how these bodies move under the influence of the force they experience. Now we're getting into the spicy part. Momentum. Translation is the motion of the particle through space. The velocity v of the particle is the rate of change of its position r. So velocity equals dr dt. Okay. For motion confined to a single dimension, we will write vx equals dx dt. The velocity and positions are vectors with both direction and magnitude. Vectors and their manipulation are treated in detail in mathematical. Yeah, I'm not gonna read. The magnitude of velocity is the speed v. The linear momentum p of particle of mass m is related to its velocity v by p equals mv. So that's linear momentum. Like the velocity vector, the linear momentum vector points in the direction of the travel of the particle. Its magnitude is denoted p. What in the hell? Okay, there are two parts. Yeah, I'm not gonna. What? Okay. Yeah. Okay. The linear momentum p is denoted by a vector of magnitude p and oriented that correspond to the direction of the motion. Motion of the ocean. All right. The description of rotation is very similar to that of a translation. The rational motion of a particle about a central point is described by its angular momentum, J. So it's basically just alphabet at this point. The angular momentum is a vector. Its magnitude gives the rate at which a particle circulates, and its direction indicates the axis of rotation. The magnitude of the angular momentum, J, is that a but or, oh, it's omega. J equals I and omega. Where omega is angular velocity of the body, its rate of change of angular position in radians per second, and I is the momentum of inertia, measure of resistance and rotational acceleration. I can't. Acceleration. For a point of particle of mass m moving in a circle of radius r, the moment of inertia about the axis of rotation is IMR2. All right. Newton's second law of motion. Damn, even Newton has motion in freaking 17th century. According to Newton's second law of what is for, isn't there as a first law? Yeah, probably. According to Newton's second law of motion, the rate of change of momentum is equal to the force acting on the particle. dp dt is equivalent to F. For the motion confined to one dimension, we will write this basically Newton's second law of motion 2.5a may be taken as a definition of force. The SI unit of force are newtons. So basically, Isaac Newton was so of himself, he made a whole SI units of himself. That's pretty amazing. 1n, okay, 1 kg. All right. Because P equals mdr dt is sometimes more convenient to write alternative form. Okay, so mass times acceleration equals force, where acceleration of a particle is its a rate of change of velocity. It follows that if we know the force acting everywhere and at all times, then solving equations 2.5 will give trajectory and the position of momentum of a particle at each instant. Okay, energy, a first look. Okay. All right. Before defining the term energy, we need to develop another familiar concept, that of work. More formally, then we preview the use of these concepts in chemistry. Work, W, okay, is done in order to achieve motion against the opposing force. For an infinitesimal displacement through ds, a vector, the work done is dw equal, okay, now they're just making it up. dw equals minus f times ds. All right, that's the definition of work. Where if f ds is the scalar product of the vectors f and ds. Holy shit. Okay, for motion in one dimension, we write dw equals minus fx dx. The total work done along the path is the integral of this expression, allowing the possibility of that f changes in direction and magnitude at each point of the part, which force in newtons and distance in meters. In the units of work are joules, J, which 1 joule equals 1 kg m2 whatever. Okay. To accelerate a rotation, it's necessary to apply a torque T, a twisting force. Newton's equation is then DJ, like a mixtape or something, dj dt equals T. So torque, the analogs roles of M and I, of V and O, and of P and J in the translation of rotational cases respectively should be remembered because they provide a ready way of constructing what? Okay, so there's a lot of freaking, okay. Holy shit, okay. Constructing what? Am I missing? And recalling equation bubble, okay. The definition of energy, all right. The definition of energy is capacity to do work. The SI unit of energy is the same as of work, namely the joule. The rate of supply of energy is called the power, P, and it's expressed in watts, W. So big W equals 1 JS. Calories kilocalories are still encountered in chemical literature. The calorie is now defined in terms of the joule, which 1 calorie equals 4.184 joules exactly. Caution needs to be exercised as there are several different kinds of calorie. The thermochemical calorie, Cal 15, is the energy required to raise the temperature of 1 gram of water at 15 degrees Celsius by 1 degree Celsius. At the dietary calories is 1 kilocalorie. A particle may possess two kinds of energy: kinetic energy and potential energy. The kinetic energy, EK, of a body is the energy that a body possesses as a result of its motion. For the ocean, for a body of mass traveling at a speed v. So this is the definition of kinetic energy. So EK equals a half m times v in squared basically. It follows from Newton's second law that if a particle of mass m is inertially stationary and is subjected to a constant force F for a time, what the hell was that? I don't rho, right? Rho, right? Yeah. Then its speed increases from 0 to F times rho divided by m, and therefore its kinetic energy increases from 0 to EK equals F2 times rho 2 divided by 2m. The energy of the particle remains at this value after the force ceases to act. Because the magnitude of the applied force F at the time rho, it was rho, right? Or was it phi? I don't remember. No, tech cube, right? What is it? Tech? No, that's tech cube. I don't remember shit. Anyway. The positional energy EP of or V of the body is energy it possesses as a result of its position. Because in the absence of losses, the work that a particle can do when it's stationary in a given location is equal to the work that had to be done to bring it there. We can use the one-dimensional version of equation 2. Okay. So this is the positional energy. So Fx equals minus dV and dx. No universal expression for the positional energy can be given because it depends on the type of magnitude of the force the body experiences. For a particle of mass m and altitude h close to the surface of Earth, the gravitational potential energy is Vh equals V0 plus m times g times h. Alright. Where g is the acceleration of free fall. G depends on location, but its standard value is 9.81 ms. The zero potential energy is arbitrary. For a particle close to the surface of the Earth, it is common to set V0 times 0. The total energy of a particle is the sum of its kinetic and potential energies. Okay, so the sum of total energy. So E equals EK plus EP. So kinetic energy plus potential energy is the total energy. That's the sum. We make use of apparently universal law of nature that energy is conserved. That is, energy can neither be created nor destroyed. Although energy can be transferred from one location to another and transformed from one form to another, the total energy is constant. In terms of linear momentum, the total energy of a particle is E equals P2 divided by 2m plus v. This expression may be used in the place of Newton's second law to calculate the trajectory of a particle. Alright, the Coulomb potential energy. One of the most important kinds of potential energy in chemistry is the Coulomb potential energy between two electric charges. The Coulomb potential energy is equal to the work that must be done to bring up a charge from infinity to a distant or from a second charge. For a point charge Q1 at a distance r in a vacuum from another point of charge Q2, the potential energy is VR equals Q1 Q2 divided by 4 times pi times epsilon 0 times r. That's the Coulomb potential energy. Charge is expressed by Coulombs C often as a multiple of fundamental charge E. Thus, the charge of an electron is minus E, and the proton is E plus E. The charge of an ion is ZE. Oh, that's us, baby. That's us, ZE, baby. With Z, the charge number, positive of cation ions, negative for anions. The constant epsilon 0 is the vacuum permittivity, a fundamental constant with the value of 8.854 x 10 minus 12 C. Alright. It is conventional as equation to set the potential energy equal to 0 at infinite separation of charges. Then two opposite charges have a negative potential energy at infinite separation, whereas two like charges have a positive potential energy. What we have here in medium, other than a vacuum, of potential energy of interaction between two charges is reduced, and the vacuum permittively is replaced by permittively epsilon of the medium. The permittively is commonly expressed as the multiple of vacuum permittively. So epsilon equals epsilon r times epsilon 0. The epsilon r, the dimensionless relative permittively, formerly the dielectric constant. This reduction in potential energy can be substantial. The relatively permittivity of water if 25 degrees Celsius is 80. So the reduction in potential energy for a given pair of charges at a fixed difference with sufficient space between them for the water molecules to behave as fluid is by nearly 2 orders of magnitude. Care should be taken to distinguish a potential energy from potential. The potential energy of a charge Q1 in the presence of another charge Q2 can be expressed in the terms of Coulomb potential phi. Oh yeah, so VR equals Q1 phi times phi. So phi is the Coulomb Coulomb potential energy. The units of potential are joules per Coulomb, JC minus 1. So when phi is multiplied by a charge in coulombs, that results in joules. The combination joules per Coulomb occurs widely and is called a volt, a V, 1V and 1J. If there are several charges Q2, Q3 present in the system, the total potential experienced by the charge Q1 is the sum of the potential generated by charge. Okay, so phi equals phi 2 plus phi 3 plus, all right. Just the potential energy of a charge Q1 can be written as V equals Q1 times phi. So the magnitude of force on Q1 can be written F equals Q1 equals big E, where big E, what the hell is that? E is magnitude of the electric field strength. Units, volts per meter. Okay. Arising from Q2 or from some more general charge distribution, the electric field strength, which is like the force, is actually a vector quantity. The negative gradient of the electric potential in one dimension, we write the magnitude of the electric field strength as E equals minus d phi or times phi divided by dx. The language we have just developed inspires an important alternative energy unit, the electron volt, EV. 1 EV is defined as kinetic energy acquired when an electron is accelerated from the rest through a potential difference of 1 volt. The relation between electron volts and joules is 1 EV equals 1.6. Many processes in chemistry involve energies of few electron volts. For example, to remove an electron from a sodium atom requires about 5 electron volts. particularly important way of supplying energy in chemistry as an everyday world is by passing electric current through a resistor. An electron current I is defined as the rate of supply of charge. So I equals dq divided by dt, and is measured by amperes. So A. So 1 ampere is 1 CS. If a charge Q is transferred from a region of potential, all right, phi, it was phi, right? Yeah, phi. Phi, where its potential energy is Q phi, to where the potential is Q, phi f, and its potential energy is Q phi f. And therefore, through a potential difference, delta phi equals phi f minus phi I. Woo! That's a lot of phi's. The change in potential energy is Q delta phi. The rate of which the energy changes is dq divided by dt delta phi, or I delta phi. The power is therefore power of P equals I delta phi, which current amperes and the potential difference in volts. The power is in watts. The total energy E supplied in an interval delta t is the power. The rate of energy supply multiplied by the duration of the interval. E equals P delta t equals I delta phi delta t. The energy is obtained in joules, which in the current amperes, the potential difference in volts, and the time in seconds. All right, thermodynamics. In systematic discussion of the transfer and transformation of energy in bulk matter is called thermodynamics. This subtle subject is treated in detail in the text, but it will be familiar from introductory chemistry that there are two central concepts: the internal energy U, unit joule, and the entropy S. The internal energy is the total energy of a system. The first law of thermodynamics states the internal energy is constant in a system isolated from the external influences. The internal energy of a sample of matter increases as the temperature is raised. We write delta U equals C times delta times T, where delta U is a change of internal energy when the temperature of a sample is raised by delta T. The constant C is called the heat capacity of the sample. If the heat capacity is large, a small increase in temperature results in a large increase in internal energy. All right. This remark can be expressed in a physically more significant way by inverting it. If the heat capacity is large, then even large transfer of energy into the system leads to an only small rise in temperature. The heat capacity is an extensive property, and values for a substance are commonly reported as a molecular heat capacity. Cm equals C divided by N. Or the specific heat capacity, Cs equals C divided by M, both of which are intensive properties. Thermodynamic properties are often best discussed in terms of infinitesimal changes, in which case we will write equation 2.I. So that's the heat capacity. We see that the heat capacity can be interpreted as the slope of the plot of the internal energy of a sample against temperature, as will also be familiar from introductory chemistry and will be explained in detail later. For a system maintained at a constant pressure, it will usually be more convenient to modify the internal energy by adding to a quantity PV and introducing an enthalpy H. Okay, so enthalpy is Entropy, an expected property, greatly simplifies the discussion of someone here. No. Chemical reactions is in part because changes in enthalpy can be identified with the energy transfer as the heat from a system maintained at constant pressure, as in common laboratory experiments. All right. Woo! Okay. Am I supposed to read all this? Like, this is just thermodynamic. Okay. Gonna skip this. This is just thermodynamic. I don't think it's very relevant. Okay, so the total energy of a particle is the sum of its kinetic and potential energies. The Coulomb potential energy between two charges separated by distance r varies as r. Oh no, sorry, 1 divided by r. The first law of thermodynamics states that the internal energy is constant in a system isolated from external influences. The second law of thermodynamics states that any spontaneous change in the isolated system is accompanied by increase in the entropy of the system. Equilibrium in the state is the state at which the Gibbs energy of the system has reached its minimum. The energy levels of confined particles are quantized. The Boltzmann distribution is the formula for calculating the relative population of states of various energies. The equipartition theorem states that the sample at thermal equilibrium, the average value of each quadratic comparison to the energy is 1.2 kT. Okay, that's a lot of equations to have. Oh. All right, everybody, wave that way, wave that way. Okay, waves, and that's it, right? Yeah. And what's the next topic? Is that like quantum mechanics? No. Okay, so waves. Wait. Okay. Waves, everybody. Its frequency, v nu, the number of times per second at which its displacement at its fixed point returns to its original value. The frequency is measured in hertz, where 1 hertz, the wavelength and frequency are related by lambda v equals v, where v is the speed of propagation of the wave. First, consider the snapshot of the harmonic wave at t0. The displacement is what? Poseidon's trifork xt varies as position x as okay. Where the A is amplitude of the wave, the maximum height of the wave is phi and is the phase of the wave. The shift of the location of the peak from x to 0, and which may lie between minus phi and phi. As time advances, the peaks migrate along the x-axis, the direction of propagation, and at any later instant the displacement is harmonic wave at t is bigger than 0. Okay. A given wave can also be expressed by sine function, which is same argument but with phi replaced by phi plus 1/2 pi. If two waves in the same region of space with the same wavelength have different phases, and the resultant wave, the sum of two, will have either enhanced or diminished amplitude. If the phases differ by plus minus phi or pi, so the peaks of one wave coincide with the truths of the other, then the resultant wave of the sum of two will have diminished amplitude. Okay. Wait. A wave is an oscillatory disturbance that travels through space. Examples of such disturbance include the collective motion of water molecules in ocean waves and in gas particles in sound waves. A harmonic wave is a wave that with a displacement that can be expressed as a sine or a cosine function. Harmonic waves. A harmonic wave is characterized by wavelength lambda. The distance between the neighboring piece of the wave and electric fields acts on charged particles. Wait, what? Yeah. Whether stationary moving and magnetic field acts only on moving charged particles. The wavelength and frequency of the electromagnetic wave in a vacuum are related by lambda times V equals C. That's an electromagnetic wave in a vacuum. Where C is, okay, alright. Which we shall normally quote as, okay, it's the speed of light in a vacuum. So C is the speed of light, basically. When the wave is passing through a medium, even air, its speed is reduced to C dash or something, although the frequency remains uncharged. The wavelength is reduced accordingly. The reduced speed of light is in a medium is normally expressed in the terms of refractive index (NT) of the medium, where NR equals C divided by C dash or dot or whatever you want to call it. Am I lagging? Bro, I'm lagging again. Hopefully not. Are we back? Are we back? Are we back? Bro, are we back? Probably. Yeah, we're back. Where was I? Where was I? The reflective. No. Yeah. Okay. So this is basically waves. All right. Electromagnetic field. All right. Okay. So I'm gonna get it quick here. A harmonic wave is characterized by wavelength, frequency, phase, and amplitude. Destructive interference between two waves of the same wavelength but different phases leads to a resultant wave with diminished amplitude. Constructive interference between two waves of the same wavelength and phase leads to a resultant wave with enhanced amplitude. The electromagnetic field is an oscillating electric and magnetic disturbance that spreads as a harmonic wave through space. An electric field acts on charged particles, whether stationary or moving. A magnetic field acts only on moving charged particles. In plane polarized electromagnetic radiation, the electric and magnetic fields each oscillate in each plane are mutually perpendicular. In circular polarization, the electric and magnetic fields rotate around the direction of propagation in either a clockwise or anti-clockwise sense, but remain perpendicular to it and each other. Alright, that's basically it. What to have to read to my next lecture. Easy peasy, lemon squeezy. So basically just matter, energy, and waves, not that. Oh, okay, here we go. Oh, yeah. This is where we get in. This is where we get in, right? Yeah, the wave. Are we back? Hello? You are we back? Are we good? Are we good? Are we good? Everybody? Bro. Brother, what is this? Yeah, it should work. It should work. I don't think my yeah, we're gonna get yeah, we're gonna keep streaming, don't worry. Yeah, it should work. Hopefully I don't lag. Yeah, okay, the freaking stream is lagging a bit, but it is what it is, man. But I was thinking that I'm gonna go live a bit later, and then I might do a little IRL stream. Who knows? Just because, just for fun. And yeah, I'm gonna end it here. So thank you for watching. Just a little reading stream, just to prepare for the lecture. And yeah, I'll see you a bit later. So